good day to you. It is morning, so good morning. It's morning for me. So I am in Edwin B. Forsythe, and I'm going to talk about, right now in this video, population dynamics. So let's do that. So population dynamics is how populations change. Dynamic, not static, right? So a population, again, is a group of individuals of the same species that interact on a fairly daily basis. And the four major things that impact population dynamics would be birth, death, emigration with an E, which is leaving a population, and immigration, which would be entering a population, and these would make population numbers change. But we're going to take a much closer look at all of that and what really influences how populations change. If you were to imagine that this is a graph and that the x-axis on the bottom here is time and the y-axis would be the number of individuals, then what you would see is it looks parabolic. It's exponential growth, and we call this a J-curve. So if a population was experiencing this, where we had growth that just keeps continually increasing at a faster rate, not a constant rate, we need to wonder why. And for this to exist any time, and we need to think about time scale, like how long is this going to exist? It can't exist infinitely. But at any point in time when this does exist, that means that growth is unfettered and resources are not limited. And that includes space. Eventually, even space will become limited in a population. So while this is possible at any one point in time, it is not possible to be sustained over long periods of time. There is no carrying capacity here. We will talk about that next. So what does tend to happen, same graph basically, except the ending is changed, is over time, these populations will stabilize a bit. So you still have exponential growth in the beginning. You still have that J-curve, but it's not a J-curve in this case. So this is going to be an S-curve, logistic growth. And what happens is there's often an overshoot and then a dieback, and then it stabilizes. The population will stabilize around a certain number of individuals. And again, this is logistic growth. So what does determine the number of individuals that about which the population stabilizes? Like, what is that number? Where does it come from? So what really that number winds up being is a measure, if you will, of the environmental resistance, along with something called biotic potential. So the environmental resistance determines the carrying capacity. Carrying capacity is the amount it can hold, right? Carrying, how much it can carry. So this is how many individuals of that population at that time, it's a changing number, that the environment can carry. The maximum, if you will, and around a maximum. So what determines that? Things like limiting factors in the environment. If there's not enough sunlight, only a certain amount of individuals can grow there. That's a limiting factor. Food, resources, depends on what organism we're really looking at. The biotic potential is if there was no limiting factor, if there were unlimited resources, optimum conditions based upon the species itself. How many individuals could there be in that population? This is influenced by things like reproductive rate. An elephant, how fast is an elephant population going to grow compared to a population of dandelions? Dandelions reproduce much faster. Elephants have a lower biotic potential. So again, unlimited resources are not a real thing long term. We need to think about that, and that's why logistic growth eventually is normally, there's other things that I have not mentioned, but normally what we're looking at long-term in populations. All right, so let's compare reproductive strategies. This is a groundsel tree, or the seeds of a groundsel tree, and you can see it there. All of these are baby plants, of course. Think about it that way. Is there any real parental investment that goes on beyond producing the seeds? Well, they have to disperse the seeds as well, so there are, this is a wind dispersed, obviously, right? You can see it's going to float right away. But beyond that, the reproductive strategy that this plant uses is not to put a whole bunch of investment into making sure that these seeds grow up and become adult plants and reproductively active and, you know, increasing the fitness level of the population, right? That's not how that's really going to go. So it's going into making the seeds and only that. So if only a couple live and survive to adulthood and pass on their genes in the population, then it's successful. So this is an R strategist involving trying to reproduce, but not so much trying to live until adulthood. So lots and lots and lots of babies. That's where we're going here. So the opposite of an R strategist would be a K strategist. And any of the birds that you see flying around, or if you take a look in the background, you see that osprey platform. These are all K strategists. They don't have hundreds or thousands of offspring. So what they're trying to do instead is they're trying to ensure that for each pair, you have replacement of, actually it's a little over 2, but think about 2 as being a replacement for a pair. And as long as 2 survive to adulthood and pass on their genes and have kids themselves, then that replacement level fertility is accomplished. So their strategy, again, is to put not as many resources into reproducing and making a whole bunch of babies, but to ensure that those babies survive until reproductive age. Post-reproductive age is not as important if you really think about it in terms of fitness, although inclusive fitness can dictate that older individuals can be, even if they're not reproducing anymore, they can, with indirect fitness, pass on their genes through family members. But that's a different story for another day. But in terms of population dynamics and strategies, K strategists like an elephant, birds, those rely more on making sure that their offspring survive. And that's where the energy goes. So what else can limit the size of a population? Well, there are density dependent and density independent limiting factors. So density dependent means that it depends, these effects depend upon the size of the population, the density of the population. For example, predation. You may have more predators if there is a larger prey population. Same thing. Disease. You will have more hosts with a larger, more dense, not just larger, more dense population. Density independent would be more like a fire or a flood. If this whole place flooded, it wouldn't really matter if you're susceptible to flooding. It doesn't matter how dense the population is. It's going to have an effect on all of you pretty equally.